we are. I'm going to back up a little bit, guys, and repeat that for the film. So here we are looking at these two balls. They both have the same mass. And I'm going to hit ball one into ball two, and we're going to watch how fast ball one is moving. We're going to ignore ball two for now. And we see ball one started out pretty fast. After the collision, it was moving slower, right? Okay? So that's the first comparison. What happens to ball one's momentum before versus after? And we can see that it loses momentum. Next thing, look closely at ball two. I want you to compare its velocity after the collision, because it's not moving before. Compare its velocity after the collision to the velocity of ball one before the collision. So the original speed versus how fast ball two goes. So you ready? Hopefully I do a good example. Yeah, that one's pretty good. What do you say? Andres, what do you think? If we compare the speed of ball one, original speed of ball one, to the speed of ball two, what did we notice? Was ball one slower, faster, or were they the same? What do you think? Andres? Are you able to talk? Maybe you don't. I see you type something, huh? Yeah, I agree, Andres. Thanks. That works. So ball one's original speed, at least, is faster than the speed of ball two, isn't it? So that means it started with more momentum than it gave to ball two. And we can kind of see that because, like Jose said earlier, some of the momentum of ball one is transferred to ball two, which means it lost momentum, but ball two gained momentum, huh? Right? So the next thing, I just want to think about this really briefly. In a way, it's so obvious that I shouldn't even mention it. And I'm using this grooved board here intentionally to maintain this issue. Remember, velocity is not only how fast they go, it's the direction they're moving. So ideally, it looks something like that. Yeah. And let's see, Kaylee, what happened to the direction component of velocity before the collision versus after the collision? What happened to direction?
Well, like on some charts, they like keep on going the same direction, but
The
like
direction did not change, did it?
No, it didn't.
So we can ignore direction in our analysis of this collision, I think. Is that okay? We can simplify our system. Remember, we were putting boundaries on the system to simplify our understanding and come to some big ideas. And part of that is limiting the number of things we're studying at any one time. If we can ignore direction, that's going to make this a lot simpler to figure out what's going on. Okay? So we had ball one speed before, ball one speed after, and we had ball two speed after. Three different things to keep in mind. And of course, the speed, because it's going in this direction, is really a velocity. And if we multiply that times the mass, we get momentum. So let's think about this. Which of these three possibilities, ball one before, ball one after, ball two after, which one of those had the most momentum? Andres? Which has the most momentum? If you guys are here, your cameras need to be on. I don't count it. I don't count attendance if I can't see you. So I'm waiting for a couple of you to turn your camera on. I'm not counting you present unless I see you, because I know some of you have just been checking in and then not participating, because I call on you and there's no response. So it's not attendance if you're not part of class, right? At any rate, we had three momentums to think about. Ball one before, ball one after, and ball 2 after. Which of those is the greatest momentum? How about it, Alejandro? Which of those three had the greatest momentum? Ball 1 before, ball 1 after, or ball 2 after?
Ball 1 before.
Yeah, because momentum is their mass, and they're both the same, times the velocity, and ball 1 before had the highest velocity, which means it had to have the highest momentum. Which one of these would have the least momentum of those same three choices? Which one has the least momentum? Gus, ball 1 before, ball 1 after, or ball 2 after has the least momentum?
Ball 1 after?
Yes, ball 1 after has the least momentum. So we can actually break this down and start doing some math with it. So can we see the board okay? It's kind of glary, huh? So here's what we're going to do. We're going to calculate the momentum for these three things. We're going to calculate the momentum of ball 1 before, ball 1 after, and ball 2 after. Now these are not exact measurements. I'm just estimating. So let's see. Ball 1 and ball 2 before and after. So remember, to calculate momentum, we need this equation, P equals mv. So we're going to use that multiple times. And to keep it straight which ball we're talking about, we're going to use a little sub symbol, like P1 equals M1 V1. Over here, it's going to be P2 equals M2 V2. Okay? The 2 just means it's ball 2. The 1 means it's ball 1. And I'm just going to give you the mass of ball 1 was 42 grams. And I'm making up this velocity, but we saw that it was faster at the beginning, so I'm just going to say it's 10 miles an hour. Okay? For ball 2, the second ball's mass was also 42 grams, and it was very clear that its velocity before the collision was 0 miles an hour, right? So what do we get here? For the velocity before the collision, we just multiply mass times velocity, 42 times 10, which is 420 miles per hour. That was before the collision. Over here, the velocity of P2 was 42 times 0, which of course makes 0. It had no motion, therefore it had no momentum. Right? Now there's one thing more I want to do here, and that is calculate the total momentum of the system of two balls colliding. If we add these two together, we will get the total momentum. And we're going to call this PB, and the B represents that it's before the collision. As you know, 420 plus 0 is still going to be 420. Okay? Now, after the collision, their masses didn't change, did they? We didn't see any chips of wood flying off of one. We didn't see any bits of wood added to another. So after, we're going to have the mass for ball 1 is still the same. And once again, I'm just going to throw out a possible speed here, which is going to be 3 miles an hour for ball 1. It was the slowest of the three, right? Over here, ball 2, still 42 grams. And I'm going to estimate its speed at 7 miles an hour because it was not as fast as the ball 1 started at the 10, but it was faster than ball 1 after the collision, right? So I hope those are reasonable numbers. So momentum of ball 1 would then be 42 times 3, and I've already put this in my calculator. That is 126 gram miles per hour. Meanwhile, for ball 2, P2 equals mv. 42 times 7 equals 294 gram miles per hour. So far, so good. We've just taken the mass times the velocity before and after. We're finding out that our greatest momentum was ball 1 at the beginning. Our least momentum was ball 1 at the end, and ball 2 after the collision was in between, right? Isn't that what we observed? But what I really want to do now is find the total momentum after the collision. So this is going to be P after the collision. And all we have to do is add the momentums of the 2 parts of the system together. The 2 parts of the system would be ball 1 and ball 2, right? We add those together and we get 420 gram miles per hour. Now, let's compare the momentum before to the momentum after. Here's my momentum before. Here's my momentum after. And what do you see? Sam, tell me, what do we see for our momentum when we compare before and after?
I'm not quite sure.
Sorry, I can't hear you.
I'm not quite sure.
It helps if you're here on time. Also, for you to be counted as a present, you need to have your camera on. So I'm still waiting for Armando and Dylan and Pat. You guys got to have your cameras on to be present. So, momentum before, total momentum that I double underlined, Sam. Find the section that has the double underline. That's the momentum before. If it says P sub B, the B is for before. P, of course, is momentum. And then find the double underline where it says P sub A, the momentum after. And we're comparing the momentum before the collision of those 2 balls to the momentum after the collision of the 2 balls. So Sam, what do you notice? The double underlined part. What do you see? How do those numbers compare?
They're the same.
They're the same. Exactly. So what do we call it if we keep the same total momentum before and after an event? What do we call that if we keep it the same? Armando, I haven't heard from you yet, and I'm not even sure that you're here because I can't see your face.
Yo, what's up?
Hey, nice to hear your voice. There you are. So
Really?
what do we call that law where things stay the same? We didn't destroy any momentum. We didn't create any momentum, but we transferred some from ball number 1 to ball number 2, right? We
Yeah.
transferred momentum from here to here, right? In that collision. So what do we call that law if we're keeping things the same? Any law where we keep everything the same always has the same name. Do you remember?
No.
Anybody out there able to help out?
Is it the conservation law?
Exactly. Good job. It's the law of conservation. Now, last chapter, we studied conservation of energy. Now we're studying conservation of momentum. Was momentum conserved in this example? Did we start and end with the same momentum? Or did we lose some momentum? Or did we gain some momentum? Or did we just transfer momentum but keep it the same total momentum? Are you with me on that? We started with 420. That was added to ball one by my hand, huh? After it collided, its momentum dropped down to 126. So it lost momentum, didn't it? But it gave some momentum to ball number two. It went up to 294. Now that means it gained momentum. However, did the system as a whole gain or lose momentum, or did it stay the same? I think it stayed the same. Started at 420 and it ended at 420. No gain, no loss, but there definitely was a transfer. Does that make sense? Anybody have questions or comments? Now, of course, I made up those numbers to make sure that conservation of momentum would be shown, right? But if we were able to actually measure what happened precisely, we would find the same thing happened. Okay? So at this point, we're going to switch to the project. So please pull up your project. And I'm going to go, let's see, where did we leave off on this? I think we're like on page 13 or 14, huh? So let's jump down to page, yeah. So last class on Monday, we went over page 12. We did all of page 12 together. Then I asked you to finish class by working on page 13 by yourself. So this should be done. We're now on page 14, where we have this new topic of collisions. Previously, we were just looking at things moving and how much momentum they had. Here we had a football player. We calculated their momentum, the letter P, momentum. We drew a vector diagram to show their motion, right? That was homework. We did the same thing here with a rolling ball. Or no, this was a car that we represented with a circle, right? But now we're going to look at collisions and what happens when two things collide. So let's look at this problem. A ball is traveling toward a stationary ball. In other words, it's not moving if it's stationary. A ball is traveling toward a stationary ball of equal mass at the given velocity. That means the velocity is going to be given to us down here in the problem. After the collision, the two balls collide and move together in the same direction. This is going to be a little different than what we saw in my example. In this case, the balls stayed together, and you can see that in this diagram. They're rolling together here. Kind of like if there was one car ran into another and their bumpers got locked and they kept moving forward together. These two balls are rolling side by side together. Now, one thing that I changed on the project here that you might want to do too, just to keep everything clear, is I added these words before and after. So I think it would be really helpful to the way you're thinking about this if you added before and after into your project too. So here, we're going to calculate the momentum before the collision. We're going to draw a vector diagram showing what's going on before the collision, and we're going to outline the boundary for the system before the collision. So all of this is what's happening before there's any collision going on, right? Then in part B, we're going to show what happens after the collision, which is a little more complex. And then they have another problem in here that's a little tricky, so we're going to do that together. Okay, so they've told us that the ball 1 is a mass of 10 kilograms and ball 2 is also 10 kilograms. Before the collision, ball 1 is moving at 2 meters per second and ball 2 is not moving at all. We need to calculate the momentum of the two balls, and I'm going to call on people to help me with this. So take a minute to calculate the momentum of ball 1. They've already filled in the beginning of it for you. Then calculate the momentum of ball 2. Third, find the total momentum before the collision. All right, so do those three things. You should be able to do this in your head pretty quickly, I think. David, please tell me the momentum of ball 1 before the collision.
20.
Yeah, simple. 10 times 2 makes
20.
Yeah. And the way we would actually say that is 20 kilogram meters per second. Really strange measurement, kilogram meters per second. But notice it includes how heavy it is combined with how fast it's moving, meters per second. Just like miles per hour, meters per second. Good job. Okay, so next let's have Dylan. Give me the momentum of ball 2, Dylan. You can either say it or you can type it. If you're having trouble with your microphone, please type the answer. Okay, I guess he's not here. Sam, how about you? What is the momentum of ball 2?
Would it be,
A little louder.
would it be 40?
Okay, remember momentum? Remember the equation for momentum is right here. Mass times velocity.
Okay,
So P is momentum.
so it's 0.
Yeah, it's 0. Perfect. Thank you. So 10 times 0, 0. Next one. What is the total momentum before the collision? Pat, you can either say it or you can type it.
20.
Yeah, simple. You just add those two together, right? 20 plus 0, we get 20 kilogram meters per second. Thank you. All right, so the next thing we're going to do, we've just calculated the momentum. We did this part, first part of 3A is done. I can put a check mark next to that. Now we need to draw the vector diagram, right? And actually they've done it for you in, faintly. They would like you to fill it in for yourself, but this is just to give you practice on how to do it. So we're going to start off with a circle to represent ball 1. And I need to draw a circle on top of that. You should too, for it to count as having been done. Just make a circle on top of it. And then ball 1, we also need to draw ball 2. And remember, they were the same mass. So we're going to draw a circle that's identical to ball 1. And the way I'm going to do that is I'm just going to copy and paste the circle I already did. So if I use Control C, or if you have a Mac, it's Command C. And then I use Control V, I've done a copy paste. Simple way to do that. Shortcut using the keyboard. Okay, so I've drawn my two masses. In this case, they're both balls. Next, I need an arrow that represents their momentum. Now, sometimes an arrow in a vector diagram represents velocity, but this is really representing velocity combined with their mass. So this one is a momentum arrow, not a velocity arrow. And they've shown it as that size. Okay, representing 20 kilogram meters per second. So we've done that. Took care of that one. Next thing we need to do is outline the boundary of the system. And then we'll be done with this part of it. So I'm going to grab a rectangle, and they're showing the boundary as this zone right here. Basically, we're not studying the ball until after it entered this boundary. And if this one goes beyond the boundary after the collision, we're not going to study it anymore either, unless we move the boundary. We have to include the space between the two balls because ball 1 is going to collide with ball 2, huh? So that's what it should look like for part 3A. I've done my momentums. I've found the total momentum before the collision. I've done my vector diagram, including the boundary for the system. All right? So now we want to find the momentum after. We're going to draw the vector diagram after. We're going to outline the boundary for the system after. But there is one more thing in here that is tricky. That's this part. We're going to calculate, using some algebra, the velocity after the collision. And this is actually where we're going to begin here. Okay? So, because momentum is conserved, in other words, the total momentum is not increased, it's not decreased, but it can be transferred from one part of the system to another part of the system, we should already know the momentum after. I wonder if you're thinking about that. If momentum is conserved, Quetzali, if momentum is conserved and we know the momentum before, what can we say about the momentum after? The total momentum, not of any individual ball, but of the two balls combined. What do you say, Quetzali? What's the momentum afterwards?
Also 20.
Yeah, exactly. Because we know that momentum is conserved, there's not a loss of momentum. There's also no gain of momentum. Therefore, after, there must be 20 within the entire system. Because we started with 20, we had to end with 20. It's conserved. Okay? Now comes the tricky part about velocity. It's going to take some algebra to do this. So, first of all, because the balls are moving together, momentum is now based on their combined mass. Okay, now I've used this blue highlighting to show the momentum after the collision, right? So that's right here in blue. For the mass, I'm going to use this pink highlighter. So mass is now combined, right? Momentum, P, equals mass times the velocity. Now they're moving together like two train cars connected with one another. So it's V1 and 2 combined. And I'm going to use a yellow highlighter for that. Okay. Now notice the question was to find that velocity. So I'm going to show that as yellow. We're going to try to isolate V. We're going to try to find out how fast they're moving. Because we don't know. We know what their momentum is because we knew how fast they started. But how fast are they after they collide? So V is in yellow, correct? There it is. And here it is. And here it is. It's measured in meters per second. So this is our final answer. It's going to be the velocity, how fast it's moving. To calculate this, we need to multiply Mass times velocity to get momentum, right? So we need to have mass in there, which I used for this pink highlighter, correct? So that's going to be right here. That's the mass, kilograms. And here it is down here, kilograms. The momentum itself I showed in blue, and that's going to be this, kilogram meters per second. Kilogram meters per second. So what's happening here? We know this equation, P equals mv. This is just a simplified way of writing it. P equals mv, right? P is right there, huh? P total after, that's P. Well, that didn't work very well. Let's get rid of that guy. I'm just going to draw it. P is right there, huh? M is right there, and V is over here. I could also use the highlighter to show these things. Let's see, P was, hello, what's happening? Sorry. Highlighter. P was light blue, huh? Maybe it's not going to allow me to highlight what I wrote on. Nope, I don't think it will. Okay, so P equals mv, but we're looking at the momentum after, which we know already it's 20, because it's the same as the momentum before, because momentum was conserved. So anytime it has momentum, I can put that 20 in there. P equals mv. Now what's the mass? The mass was the mass of, oh, the two balls combined now, huh? So how heavy were they? They were both 10 kilograms. So my mass is also going to be 20, but this time it's their mass, not their momentum. Personally, if I had designed this question, I wouldn't have made these two numbers match, but that's okay. Now, the whole thing that has to happen here is we have to get velocity by itself. It asked us to find the velocity. So using algebra, if we have m times v, we're going to have to divide both sides of the equation by m. So we're going to divide this by itself. It cancels out, but we got to divide it over here too. So that's what these parentheses are showing, that we are dividing the momentum by the velocity. So the momentum was 20. The velocity also happened to be 20. And that's why I would have preferred to have two different numbers, but that's okay. And 20 divided by 20 equals 1. Is that right? My answer is 1 meter per second. That is my velocity, 20 over 20. 1 meter per second. Let's see if that makes sense. Before the collision, ball 1 was moving at 2 meters per second, and the second ball wasn't moving at all. After the collision, they stuck together and kept rolling at 1 meter per second. Does that make sense that they would have slowed down when they have more mass to move? I think that answer does make sense. So next we need to draw the vector diagram, including the boundary of the system. So our balls didn't change at all. I'm just going to click on this circle I already drew, and I'm going to copy it and paste it. And I'm going to drag it down to this part of the page. I'm going to put it right there. I'm going to do the same thing again. I'm going to copy that and paste it and put it right there. Now I have two equal circles, and all the circles I've drawn are equal because I copied and pasted. I didn't have to worry about resizing them or anything. So the two balls are stuck together. They're both 10 kilograms each, making a total of 20 kilograms. And they're moving forward at 1 meter per second. Now this is where we have to be careful with our arrow, because the arrow is not only showing the velocity, it's showing the momentum. And remember, the momentum after was 20, just like it was before. So actually, I need this same size arrow to represent momentum. So once again, I'm just going to copy and paste. I like to use the keyboard shortcut, Control C, copies, Control V, pastes. And I'm going to put it right in the middle to show that they're both moving together. The last thing I have to do is draw the boundary of the system. I'm going to use a little bit of room from showing where ball 1 came from and a little bit of room to show that they're going to continue traveling out in that direction. But basically, that's the limit of my study, is that boundary. I can't study every single detail. I'm not going to include the friction that they have with the floor. I'm not going to include the slope of the land. So I have to limit what I study. Okay, so that's actually all that we're going to do with the project. I would ask you at this point to give me a thumbs up if you're done with that and if it made sense. You can either show me your thumb in your camera, or thanks Kitsale, thanks Alex, or you can give me a thumb up in the comments. Thanks Pat, thanks Sam, there you are, hey man. Thanks Gus, thanks Andres. Okay David. We are going to switch over to the collision document then. We're not going to work on the project anymore today. We're going to work on the collision assignment. All right, thanks guys. So switch over to the document called collision. So it should look like this. So get that ready to write into. And like I said, I made a mistake in the first version of this document, and I posted the old document. So we have to make sure you have the right one. And all you have to do is look for this and this number. If yours don't match that, then you have the old version. And actually, you don't have to download the new one. You just need to change your numbers to match these numbers. Just change yours to match. If yours say 10 and 4, then you're in good shape. If they don't, you can just scratch it out and then type in what it should be. Okay? Okay. So I want to make sure everybody's ready. Give me another thumb up if you're ready to move on. All right, Alex, thank you. Thanks, Sam. Thanks, Kitsali. Thanks, Gus. Kaylee, are you ready? Thank you. Thanks, Pat. All right, Jose, thank you. Okay, so this one's more of a real life example. Don't worry, no one was harmed in the making of this worksheet. So a 1,200 kilogram car slows and stops when a light turns red. The driver of a 1,500 kilogram car behind them is checking a text on their phone, and they rear end the stopped car at 12 meters per second. The car in front gets pushed forward at 10 meters per second, while the car that caused the collision rolls forward at 4 meters per second. So what I want to do first of all, maybe you can figure out all these things yourself. That'd be awesome. You can go ahead and move faster than me if you want. We're going to do the same things we were doing before. We're going to calculate the momentum before the collision. We're going to draw the vector diagram. We're going to outline the boundary for the system. But it might help if I do some highlighting on my document. So let's see, I'm going to make car 1 in blue. And car 1 is the car that's stopped. Okay? So it's the stopped car. Meanwhile, car 2 is going to be pink. And that's the one that weighed 1,500 kilograms. They're checking attacks. They rear end the stopped car. Oh, and they were going 12 meters per second when they collided with it. And I think that's all we need for the before part. The other information we need for the after. I might as well highlight those while I have them. The car that caused the collision kept rolling at 4 meters per second. The car that was hit ended up moving at 10 meters per second. Okay? So I'm going to give you a couple of minutes to do all this for yourself. I'm going to turn on some music, and that's going to be my timer. I'm going to choose a song that's about 5 minutes long, all right? So ready, set, and go. Let me know if you have trouble, if you're stuck on something. Either talk to me or write me a note. And give me a thumbs up when you're done. Do the vector diagram also. Okay, how are we doing out there? You should be done with the math and with the vector diagram. Don't forget to draw the boundary of the system. Let's see. I saw Sam was done. Anybody else finished? Okay, thanks, Alex. Thanks, Kitsali. All right, Kaylee, thank you. Just so you know, the number that I chose here of 12 meters per second, that was that's a little faster than 25 miles an hour, just so you know. So I was trying to have realistic numbers. I also looked up how heavy cars are, and these are reasonable masses for cars. And just in case you don't know, kilograms are bigger than pounds. So this car, let's see, it's like basically multiply times 2.5. So it's like 4,000 pounds. This one would be about 3,000 pounds. Okay, so I'm not going to give you the answers on this. I want you to do it for yourself. But I am going to give you a way to check your work. And what I'd like you to do now is we're going to move on to, thank you. We're going to move on to part 2, where you're going to find the momentum after the collision. And once again, you're going to draw a vector diagram. In this case, they didn't stick together. So the first one we drew over here, they were side by side because they're stuck together. In this case, one is moving faster than the other, right? So your vector diagram shouldn't look like this for the after part. We're not going to calculate the velocity. I just gave that to you up here, right? And I highlighted the different parts to show which car was which. So I would like you to move on, calculate the momentum of car 1 after the collision, momentum of car 2 after the collision, and find their combined momentum, the P total after the momentum of the two cars afterwards, for the entire system, in other words. Okay? So basically you're repeating what you just did with different numbers, huh? And then the vector diagram will look a little different too. So go ahead and do that. Once again, I'm going to give you about 5 minutes to work on it. If you have questions, please let me know. If you're stuck on something and don't quite know how to do it, I'll be happy to help. Now, although I'm not going to give you the answers to these, I will tell you that you can tell if you've done the correct thing or not, because the conservation of momentum should take place here. Basically, if you've done the right thing, you should have the same total momentum before as we have afterwards. So you can kind of feel confident about your work if you got those two answers the same. And give me a thumbs up when you're done. Thanks, Katsali. Is that Sam doing this?
Yes.
Thanks, David. Thanks, Alex. Kaylee. Jose, thank you. All right, Gus. And do something else for me, guys. I would like you in the comments to put in like some kind of happy emoji if, like I mentioned, if you ended up with the same total momentum before that you calculated after. Did the problem work out for you where we conserved the momentum? So give me a happy sign of some sort. It could be emoji, it could be a GIF, something to indicate that they were the same. Nice. All right. Good job, you guys. Way to math it up. Yeah, I know. You thought this was science class and we're doing this math all the time, but that's largely because this is physics. And in physics, we can define things so specifically by drawing boundaries in our systems that we can actually do the math. It's much harder to do for something like biology. How do you do the math of the way that your heart is pumping, for instance? I guess you could do some math problems, like measuring your heart rate before and after exercise, for example, but it's trickier. Yeah, BPM, exactly. Okay, so if you got the same two answers here, that should make you feel really confident in your work. Hopefully you've drawn your vector diagrams and you thought about what we were talking about. I do have one hint for you here on the vector diagram. I want to remind you that one car was bigger than the other, right? So you should not have equal size shapes to represent these cars. You could draw a car. I noticed that some of you did that before. That's great. You could use a circle. I'm going to use a square. So let's see. The car in back was bigger and it was 1,500 kilograms. And I noticed that I have 3, and if I count by 5, 3 by 5, 3 times 5 makes 15, and that would nicely represent 1,500 kilograms, huh? So I could show this car to scale. I'm going to fill it in and make it red because that was the color I used to represent car 2, right? It's the one in back. Meanwhile, this one was 1,200 kilograms. So if I want to draw this to scale, I need to choose 12 boxes, which is 3 by 4. Works out kind of nicely. And I want to make this one be blue. So I'm going to go to properties. I'm going to change the outline to blue. I'm going to change the fill color to blue. Boom. Now I've shown this car bigger than that one and exactly the right amount bigger too. It's that much bigger in mass, right? I mean, it's not exact because they don't line up, but it's pretty close. right? This one's 12 boxes to represent 1200. This one's 15 boxes to represent 1500. Then I need an arrow to represent my momentum. Each one should have its own arrow. So this one, car 1 in the front, it was not moving, so it gets no arrow, does it? Down here, it will have an arrow. Car 2 up here should have an arrow. And whatever that momentum was is what I'm going to draw here. I'm going to make it be 3 boxes long. I'm going to measure how many boxes long it is. Because down here, the 2 combined arrows should equal 3 boxes. I think if you did your math right, you would find that one of them would be 1 box long arrow and the other would be a 2 box long arrow down here. Because the momentum total was the same, but it got distributed. Some of the momentum got given to this box, got given to this car. So think about that. Try to make things to scale, and you can make adjustments if you need to. A couple more things that I need to do to finish. Since I'm doing this one with you, we'll just finish this one up, and you can make sure you're on the right track. I'm going to type in here, just to make sure I know what I'm talking about, car 1, and I'm going to type in that it was 1200 kg. You should do the same thing down here. I'm not going to do this one for you at all, but the same things I'm doing up here, you should do now, and then do them down here. Meanwhile, I need to do car 2, and it was 1500 kg. And I don't think that red on red is going to work very well, so I'm going to change that to blue on red. Then I need to label the momentum of each car individually. So P1 equals, and this is what I'm not going to write in, whatever you calculated here, you should put that over here for car 1, And the same thing for car 2. P2 was how much? What was its momentum? And finally, over here, let's label somewhere. It doesn't matter if it's here, it could be in the middle, it could be on the left, it doesn't really matter. I would like you to write down the final momentum, which we're going to call P total. Okay, so you're going to fill these in for yourself based on what you calculated here. Same with this one, right? We should include all these labels in your second vector diagram too. The one thing that I was almost forgetting to do is drawing the boundary of the system. So I need to make a box that's a little bigger than the space that these are in. And to make this show up, I'm going to change its color just so it's a little different. I'm going to make it green. So this is what your first vector diagram should look like, except that you need to have these numbers filled in, right? Everything's labeled. Really, a good place to put this one would be right there, with the actual arrow showing that momentum. But it's okay if you put it with the car, that works too. So have your second vector diagram down here set up similarly to this one, where car 2 is obviously bigger than car 1. It doesn't have to be as accurate as this one is. This one's pretty accurate because I made it 15 boxes versus 12 boxes. If you can do that accuracy, that's nice, but you don't have to. Just make sure that it's clear that car 2 was a little bigger than car 1. Label their masses. Label their momentums. And then label the total momentum. All right? When you're done with that, you'll be ready to answer these questions, 3 questions. And I think you can do that on your own. So that's all I have for you today. Does anybody have any questions for me? If not, you can exit. It looks like we have another, 15 minutes of class because it's a short class today? Something like that? So, not even actually, because there's nutrition today too. Thanks for hanging with me, guys. You are free to go. Please let me know if you have any questions. Send me an email or send me a comment on Teams, all right? Get that done and turn it in. Turn it in 2 places, in your notebook and in the assignment, please.
See you, Fairly.
Thanks, Fairly.
You're
Thanks.
welcome.
See you,
Thank you for
Fairly.
being here.
Bye, Fairly.
Later.